Thursday, we do have your first test. It is on Scantron. It is after we had a meeting yesterday afternoon and finalized, all the people teaching the classes, the we I'm referring to, finalized edits on a test, and it is going to be 21 questions, all multiple choice, 5 points each, so if you get them all right, you have 105%. Well, 105 points, but I'll put it out of 100, so maybe 105%. Let's see. Topics are everything we've talked about, including, we're going to do some kind of an extension of some things that we've already talked about, average rate of change, today in class. It'll include a little bit extra beyond what's on the test, but it's cool stuff that's kind of linked to the major underlying part of what we've been doing with constant rate of change, how you'll see it in calculus. So that's why it's not on this test, because it's a little bit beyond what we're really doing here, but it's a good review and intro at the same time. Review of what is on the test, intro that we already talked about, intro to what you're going to see eventually down the line with this. So that's what section 3.7 is, and I put in, and I know the resolution, and that's a little weird, it's very hard for me to see, but the stuff that you see due on Wednesday, the lesson and the homework from 3.7, which the lesson we're going to mostly do it in class today, and the homework is like 5 questions. So I picked out the questions from that section that are most pertinent to reviewing average rate of change, which is one of your test concepts, as opposed to the stuff that's beyond. But there's just a little bit of it in there. So in any case, what I want to do first was take a look at your 3.6 homework that's due tonight. 3.6 was about we had inverse functions. And we talked a lot about these in class on Thursday last week. But I want to spend a little bit more time just kind of making sure we've got these sorted out, what's going on. So functions and inverse functions. Functions, like the notation aside, just functions, they perform some operation. You give them an input of some type, whether it's a side length of a square, or a number of seconds that have elapsed, or whatever sort of thing you might be computing. It does some computation, and then you get an output. And the computation, we talked about this when we were doing compositions of functions. The computation might be a single step, might be multiple steps, but all of those can also be undone. And if you undo them in the reverse order, kind of like you would in algebra to get back to the variable that's hiding in the middle of the formula, what you can do is create an inverse function. And it's fairly simple when it's like 1 or 2 steps. You can kind of see what's going on. But it's when they get longer, they're a little bit more complex. We're not going to spend a lot of time on making complex inverse functions, because generally speaking, that's not something we need to worry about. It's generally just a few steps if we're interested in undoing it. Now, that's this class. Going on in lots of other classes, sometimes there are procedures that are much more involved than simply like oh, subtract, divide, take a square root, you know, kind of undo some simple operations. And there's whole classes devoted to how to do processes backward to undo or recreate the initial state of something. Differential equations is one of those classes, if you've heard of that. Comes after calculus. It's about how to undo lots of the crazy things that you learn how to do in calculus. It's like whole sequences of courses. Lots of things are very difficult to undo once you've done them. Or seeing an end result, it's not easy to recreate where we started from. But the things that we generally want to write inverse functions for are much simpler than that. So don't think I'm trying to simplify this topic and take the hard stuff out of it. It's just that we generally don't need to do this with extremely complex, weird things. So I looked through what your scores were on this, those of you that had started the 3.6 homework already, and most of you did really well on them. Some of you finished with like 100%. Let's see. That was a composition of functions thing. Oh wait, did I open up the wrong one? Oh no, this is the composition of functions. Oh, I was thinking of 3.5. No, 3.6. Inverse function things are in here someplace. There we go. So I just want to go through this whole, the notation part. The notation is the part that's the weirdest, I think, with inverse functions. So we have things that are typically written as formulas, especially when it's like area, perimeter, volume. Lots of times you just have like a single letter to represent whatever piece of the formula you need. When we go and write in function notation, it makes the writing of inverse functions more complex, but the formula part is still the same, the like function rule. So if I have a formula y equals 6x plus 11, tells us how x and y change together, tells us how x and y are related, however you want to state that. Now, the first thing it says, define a rule for a function f that determines y in terms of x. That's a lot of words just to say write the same thing, because determines y in terms of x means my formula should involve just the letter x, and the output from the formula should be y. So that's exactly what we have written here. 6x plus 11 is a formula in terms of x whose output is y. So function f with an input of x would just be 6x plus 11. Now, so that seems like a weird question to ask. But the reason for that is because of the following questions, just to make sure you understand the terminology of that really wordy way to explain do that. So if we want to solve this equation, y equals 6x plus 11 for x, that's something you've seen those instructions multiple times throughout math history. It just means, oh, get x by itself, make it look like x equals something. So we're going to solve this for x, and this is a two-step solve, right? It would just be subtract 11 and then divide by 6. So if I want to do that, like typing it out in a single line, I might want to be careful and use parentheses, or let me use the math pad here. I'm going to do y minus 11, and then I'm going to divide by 6. So I want that to be in a fraction because I want the whole thing divided by 6. Or I could write times 1/6, or I could just write it in parentheses, y minus 11 in parentheses, divided by 6 / 6, which is what it looks like if you go back out of the math pad again. That means the same thing. This is solved for x, meaning x is by itself. And here's that wordy description again. Define the rule for a function g that determines x in terms of y. So just like the original description at the top of the page here and part A, we're basically like, oh, just copy this down. So I had y equals 6x plus 11, a formula that calculates y based on having a value to sub in for x. It's a formula with just x's in it. And then this is a rule that determines y in terms of x, determines this value, 6x plus 11, which is y, because it says so right there, by just using x. Yep, that's the only unknown to plug into in that formula. Same thing here. Define a rule for function g that determines x in terms of y. Well, x equals, according to our last answer, y minus 11 over 6. So this is a formula that gives me an output of x by substituting in just a y and doing a couple of computations. So I would just have the exact same thing here. In fact, I'm just going to copy and paste. So g of y is y minus 11 over 6. So function f takes the value of x and turns it into y. Function g takes the value of y and turns it into x. And y and x, there's only one rule in this, it's just written a couple of ways, that tell us how x and y are related. Up at the top, in the original instructions, we have y equals 6x plus 11, but we know that's equivalent to just a different algebra rearrangement of x equals y minus 11 over 6, the answer to part B. So there's only one relationship between the two of them. We can rearrange it in different orders, but one of them is useful if I want to determine y and I already know x, and the other's the other way around. It's useful if I want to find x and I already know y. So the different ways to rearrange that relationship are called inverse functions to one another. One undoes what the other does, if you want to think of it that way, or they take opposite pieces of this known relationship to find the other piece from that. So any of these for part D are true. All of them are true. G undoes the process of f. G is the inverse function of f. F is the inverse function of g. Those are always true. If one function other than, there's some issues with domain. Now, domain is something we kind of like touched on really briefly. I'm not going to have a question about domain on your test. It's something we're going to deal with a lot more kind of as the semester goes on. Domain is like what values are you allowed to use other than domain issues. If one function is the inverse of another, then that other is the inverse of the first. So if one undoes the other and so forth. Why I bring up domain is you could have different denominators where there's different things not allowed, or square roots where there didn't used to be a square root, things like that. But that's something we'll deal with later. But other than that, functions are inverses of one another. So we can just say, as much as we can say it with notation, either of those two ways, g equals f inverse or f equals g inverse, f and g are inverses of each other. It's a two-way street here. So in terms of just the notation and the letters, here we go. Now, one thing I wanted to point out, in reality, when you're writing a function rule, it doesn't really matter what letters you use. So if I said, I'm just going to write this up here, if I said g of y equals y minus 11 over 6. If I were to say something like g of t equals t minus 11 over 6, these two formulas, when you plug in a value, you get the same pairs of values. The only difference between these is if there's a specific meaning that the person reading it has for what t stands for, what y stands for, etc. The symbol that you use as the input to a function isn't really the important part in the end. But if we're talking about specifically a relationship between x and y, and especially if we have something like that up at the top, or if it's maybe perimeter and side length, or something about volume and who knows what, time, maybe you have specific letters associated with this, and we'll continue using those letters. But sometimes you'll see if there's generic x's and y's, you'll just all of a sudden see everything x's as the input to functions, just because x is the normal thing written as an input. It doesn't mean we've suddenly gone around backwards and switched anything. It's just, it doesn't really matter what letter I call this. If I'm replacing it with numbers, these two have the exact same pairs of inputs and outputs. So it could just be a general letter used as it's a placeholder for whatever you're plugging in. But I generally don't like to do that if there's a specific story about the letters involved. So just to point that out. All right, let's see. So in this question 6, I'm going to make this a little bigger if I can. There we go. A is pretty much similar to the question we just did, level of difficulty wise, the formula type. Take a look at 6b here. Given that g of u equals 3u plus 7 over 4 plus 16, and the output is called v, so it's like the x's are in there, and then it's also equal to y. Find a function rule for g inverse. And it said it's calling it g inverse of v for the same reason we called the previous problem we did f inverse of y. But take a look at this b. See if you can rearrange that to solve, to isolate the u, is what we're trying to do here. So just some algebra practice, but algebra with some notation that's telling you what to do. And notice you don't have to simplify anything, make it look pretty. Anything algebraically equivalent in iMath or in math in general is fine. All right, so for this part B, and you can think of this as like V equals 3u plus 7 over 4 plus 16. Yeah, come on, there we go. Let's see. There we go. I told you to make this larger. And that turned into a capital V. All right, so V equals this whole expression. 3u plus 7 over 4 plus 16. If I wanted to solve for u, any idea, what's something you could do first? Yeah, or do you have the whole?
Oh, I have the whole thing.
Okay. What do you have for the expression part? U equals?
It's going to be 4 times u over 3.
All right, u over 3.
Minus 7. Oh,
What?
and then I guess everything should be in parentheses, and then minus 16. I did not see the 16 there.
Yeah, so there's a 16. So that 16 is going to cause us a little bit of a problem here. So we've got several steps going on, but let's take a look at this and see if it does what we want. So if I were to substitute in a number into G, order of operations wise, I would multiply by 3, add 7, divide by 4, and then add 16. So if I want to make an inverse function, you can think of it like, okay, we need to solve for u, so get this u by itself. You can also think of it as like, that was a series of steps. We need to undo them in the reverse order, kind of like you get dressed in the morning, underwear's on first, clothes on the outside, coat over the top, etc. If you're reversing that process, coat comes off first, not the underwear. So if I want to do this process first, and the last thing order of operations was add 16, we're going to need to undo that part first. Or you could get common denominators and do something with, make it all into a fraction if you wanted to. But here, oops, and I used a u instead of a v somehow. So let's think about that. But the steps in finding g of u would be multiply by 3, and then add 7, and then divide by 4, and then add 16. So if you want to reverse those directly, start at the bottom and work your way up. So I can start with my u equals, and it keeps capitalizing. Start with my v, and then I'm going to subtract 16 first, and then divide by 4, or multiply by 4. So and then subtract 7 from that result, and then multiply by 3. So if you can see the steps like that, and it's not easy if you have something like, and then take a reciprocal, like the 1 over x we talked about last class.
Divide by 3? Yeah, divide by 3.
Oh, yeah, divide by 3, sorry. I see times 3, and I was doing this fast. Divide by 3. So, yeah, we've got 4 times our v minus 16 minus 7 over 3. So I think that's pretty similar to what you had over here, only you hadn't seen the 16. But how that gets incorporated is at the beginning. Because in the original function, it was the last step order of operations wise in terms of if you were evaluating, plugging in a number for u, that would be the last thing you do. So when we're undoing, we have to do that first, deal with it first. So other than that, we had everything right in that. So the right sorts of undo steps. But yeah, our relationship here, now notation-wise, it was written in function notation. So g of u takes u and does these 4 things in sequence to it. So this, I can call this u in terms of v, or I can call it g inverse, and don't have fancy notation. Don't do that. G inverse with v as the variable apparently, since I've used v's. But again, if I call that g inverse of x and put an x where the v is, it would have the same effect. It does the same sorts of input-output matches, like input-output value pairs would be the same regardless of what I call the variable. But in order to match it up with this problem, I'm just using the v so that it makes sense and you can see what we're talking about. Sometimes in like advanced math books, just to distinguish that, they'll just do something like this and they'll have some random symbol that they use there. It's like, all right, so that we don't worry about what the letter is and just focus on the structure of the function. It's kind of a weird process or practice, but in any case, oops, g inverse of v is this v minus 16 times 4, subtract 7, divide by 3. All right, so in any case, this inverse function assignment, that one's due tonight. Make sure you finish it up if you haven't already. There's some kind of mix and match with compositions of functions for a little bit of review while you're doing this. And compositions with inverses. I did want to point out that one because we hadn't done that combination of things before. But this is just 7, right? Yeah, 7. And your numbers may be different, but it's the same sequence of things, like a composition of regular functions, some inverse functions using a table, and then an inverse composition. Just a little maybe tricky to think about, but just making sure you understand what's going on here. So the idea, again, is this is values of x, f of x, and g of x. So input x and output with either functions f or g. So if I want to find f of 5, I find 5, the input value, and go across to function f's column, and I see the number 4 there. So f of 5, start with 5, go across, and here's 4. Now, f inverse of 5, I'm not using that same thing. F inverse of 5 means, another way to think of it, I'm just going to use this as a place to type, because I can type right here. F inverse of 5 equals something. Let me call it just a random letter. That means the same as saying f of p equals 5. So if f inverse of 5 is p, then f of p is 5. So I need to find the value of p that makes this true. So f of what comes out to be 5 is what this is asking us. Because I don't have values of f inverse listed here. All I have are values of f. F inverse of 5 is saying the output from original function f is 5. What was the input? So that comes from this last line in the column here. F inverse of 5 is 11. Or if the output from function f was 5, what was the input? So it's 11. Or in other words, to replace that p, f inverse of 5 is 11 because f of 11 is 5. Now, this answer blank isn't supposed to have all of that in it. It's just supposed to be the 11 part. I was just using it to write out the explanation rather than pulling up a Word document again. But yeah, so the answer to this one would be 11 because f of 11 is 5. And I think I still have a space there. There we go. So see what you can do with C and D. C on my version is asking for G inverse of 4, and D is F inverse of G of 4. All right, what about C? Anyone want to just shout out an answer? G inverse of 4 is 7. Because G of 7 is 4, right? G inverse of 4 is 7. Comes from this line here. Because G of 7 is 4. We're not using the x value. We're using just the G of x and the x there. 4 and 7 are related, where in the original function g, an input of 7 gives us a 4. So in G inverse as a function, even though I don't know a formula for it, I know that G inverse of 4 would give me back 7. So what then about D? Again, we've got a 4 in there. F inverse of G of 4. Any thoughts on this one?
1/7?
It's not a reciprocal. It's got to be a number from this table here. But what about, start from the inside and work your way out. What's G of 4? 7. All right, so G of 4 is 7. That comes from the top row of this table. And then I saw a hand up. What's the final answer then? F inverse of 7, which is 7. And that comes from this, which is a little bit confusing because it's the same number twice. But F inverse of 7 equals 7. It comes from the fact that F of 7 is 7, so F inverse of 7 is also 7. 7 turns into 7, 7 turns back into 7. But we use that at all because G of 4, first step here. So composition of functions, you work your way from the inside out. Do the inside part first and then go outside from that. So G of 4, we found the answer to that is 7. And then F inverse of 7, where was F equal to 7? Here. What input corresponded to that? Happens to be a 7 again. So this is the 7. That's the answer that we're putting in that last blank, I guess you could say. All right, so, oh, time to get up, I guess. Pretty sure I turned that off, sorry. All right, good thing I woke up a little bit earlier than that. In any case, let's go back, and what I want to open up is something else that I have set for you. The 3.7 lesson that's due tomorrow night. I actually want to go through that, like I said, today in class. This is what's called a difference quotient. A difference quotient, those words, difference is subtraction, quotient is division. We did subtraction and division probably the second day of class. How do you find slope? You subtract, change in y over change in x, divide the two. That over is their division. That's a difference quotient. All difference quotient is that sort of structure where you're doing subtractions, two different differences, and dividing them. And the way that we normally use that is specifically for things like finding slope, finding applications of slope, such as average rate of change, that we talked about also early on. I think that was during the week I was not here. Average speed. But yeah, finding constant rate of change, finding average rate of change, finding slope of a line, those are all computations that are called a difference quotient because it involves two subtraction results that are divided. So that's all that word means. Now, a specific use of this is sometimes for the way that the phrase difference quotient is used, as opposed to just like, well, why didn't we just say slope, is if I want to be more general about it. If instead of talking about a slope between two specific points, or the constant rate of change for a particular linear relationship, where it is a line the whole time. If I want to find something where I want to talk about an average rate of change kind of as a general thing where it may or may not be a straight line or constant rate of change situation, we use this phrase difference quotient. So what I mean by that is, let's see. Suppose I have a function like this, f of x equals x squared plus 5x plus 2. That is not a straight line, correct? That's not something where I'd have the same slope between any 2 points. I can find an average rate of change or a slope between 2 points, and then I pick a different 2 points, I'll probably get a different slope. Pick a different 2 points, and I can get a different slope, and so on. What a difference quotient is something where you write kind of like a formula for what the slope between generally 2 points would be. So this phrase difference quotient is often used in that context. If I want to write a general equation, and how it's normally structured is between a generic point x over the next h units. And so we talked about function notation, and we talked about how much does the let's see, the water in the sink drain over a 3-minute interval between starting at time 2. And it's like, oh, time 2 to time 5. So we do the height of the water in the sink at time 5 minus the height of the water at the sink at time 2. That wasn't a quotient, that was just a difference. But if I want to find an average rate at which the water in the sink was dropping or whatever, even if it wasn't something that was constant, if I have a formula, I can express that as a function. So I'm just going to zoom in here so you can see this. This function f of x equals x squared plus 5x plus 2 gives us the altitude of a plane measured in thousands of feet in terms of the number of minutes since it's been off the ground. So weirdly, at time 0, this is 2, so 2,000 feet off the ground to start. So this plane is launching from someplace. I guess it's feet above sea level, so it's in a mountainous area. But if I want to know the plane's altitude 1 minute after lifting off, 5 minutes after lifting off, things like that, that's just, use the formula. And this says 1,000 feet afterwards, so you don't even have to do anything in specific. But if I want to talk about question A, just so we have some numbers to work with here. X squared plus 5x plus 2 is the formula to compute the altitude of the plane after X minutes, and the answer comes out in thousands of feet. So if I want to know the plane's altitude after 1 minute, all I'm doing here is plugging in 1. So probably do that without a calculator. 1 squared plus 5 times 1 plus 2. 1 plus 5 plus 2 is 8,000 feet, right? After 5 minutes, I'm going to have 25 plus 25 plus 2. 52,000 feet. So if I want to know the change in the altitude, what's the computation that I do to find the change in the altitude? Well, that's our difference, not a difference quotient, just a difference. Like, it was 8,000 and it went to 52,000. And notice this says 1,000 feet afterward also, so I don't have to keep that in there. I'm just going to subtract, right, a difference. 52 minus 8 is 44, and it says 1,000 feet afterward, so just 44,000 feet. Did I hit a space or something? It's weird, it has a period there. So 44,000 feet is how much it increased. Over how much time did that increase happen? Well, that's not the next question here. That 44,000 feet happened between 1 minute and 5 minutes. So that happened over a period of 4 minutes. 44,000 feet over a period of 4 minutes. So I know that the plane's average rate of increase in altitude, 44,000 feet over 4 minutes, would be 11,000 feet per minute, right? Just divide. That's its average rate of change over that specific interval. Now, if I picked not 1 and 5, but some other points in time, it probably wouldn't come out to be 11 anymore. It'd probably be something else, because this isn't a linear formula. It's not a straight line, it's a parabola. Meaning, as I go farther to the right, just thinking about things you know about parabolas, and this one in particular, as you go farther to the right, it's going to get steeper and steeper eventually, right? So thinking about rate of change, this plane's going up faster and faster. Eventually, we've got to stop using that formula for it. But this difference is part of a difference quotient. That difference is part of an average rate of change. Function notation-wise, all we did here is to find that 44. We did y final minus y initial, f of 5 minus f of 1. F was the name of the function. We're looking at time 1 and time 5, right? If I wanted to find that average rate of change and just represent it using function notation, that average rate of change is just, change in y over change in x, just like a slope. it's the same expression, but over 5 minus 1 or over 4. I'm going to write it as over 5 minus 1. All right? Even though I can do that subtraction. I can do f of 5 minus f of 1 also. In our case, that would be 44,000 feet over 4 minutes. I don't know if I just said seconds a while ago. I felt like I said seconds. But that average rate of change is 11,000 feet per minute. Now, I'm going to currently have to write that because it doesn't have 1,000 in this answer. It just says feet per minute or minutes or feet. But the units from it just come from, oh, what were the units on this? This was the 44,000 feet that the altitude changed. This was 4, 5 minus 1 is 4, minutes that went by. So feet over minutes is feet per minute. Average rate of change, any sort of rate of change, if you're doing a division to get it, the units are just the division of the two units, the quotient of the two units that you started with, the ones that you divided. So whether it's feet per second, liters per day, whatever sort of rate you're computing, the units on it come from the rates of the two things you divide in order to find that rate. So in this case, it was altitude and time, but the measurements on those were thousands of feet and minutes. This is the closest one we had, so we just put it in the 1,000. So average rate of change, as I said, this one here, this is not a constant rate of change situation. This is not a linear equation. It's not y equals mx plus b format. It's a parabola, not a straight line if I graph it. So again, what average rate of change tells us is essentially, it tells us the constant rate that you'd have to accomplish the same thing in the same amount of time. So just like if you're driving down the highway, you can go at a variety of speeds, but if you get 200 miles in 4 hours, then your average speed would have been 50 miles an hour. Because if you went 50 miles an hour for 4 hours, you'd go 200 miles. It's probably not exactly what you did. It's hard to keep a constant speed on the highway for that long, but that's how we find average speeds and other sorts of average rates. We don't find that, it uses the word average that in, it's called discrete situations. You get average test score. You add up a bunch of test scores and divide them by how many there are. Averages of heights. You take everybody's height, add them up, and divide by how many people there were. But if I talk about average rate of like how fast I was going up, 1,000 feet per minute, I'm not averaging a bunch of heights, I'm not averaging a bunch of speeds, and I have a formula that even if I'm just thinking between time 1 and 5, how many different times are there between time 1 and 5? Well, there's infinitely many. I'm certainly not going to find the average rate at which the plane is increasing in height by taking all of those different speeds, all infinitely many of them, and averaging them. That's not something we can do. So to find an average rate of change, in this case, the rate of ascent of the plane, we just do the change in y over change in x. Do a slope computation instead. And so it seems weird to do that when you see this word average. Average triggers to add them up and divide. But average rates we find differently, because we can find an average rate by looking at what's the constant rate of change that would have accomplished the same amount. Find the final minus initial for the whatever the y and the x equivalent are here. In this case, it's the height and the time. It could be weight and, I don't know, day. It doesn't really matter what the units are. The input and the output of the function whose rate of change we want to know average values for. So it involves these difference quotients. Like I said, difference quotient just means we're doing subtraction and then we're dividing. So change in y over change in x, perfect example of a difference quotient. But if this question had not asked about, well, what's this average rate of change between time 1 and time 5? what if it said, what's the average rate of change of the plane's height between time 5 and a mystery time that's h seconds later? Like, well, let me pull up my writing thing here. What would it said? Find the average rate of the, let me do this. The plane's change in height between time 5 and another time h minutes later. So 5 minutes are input to this function was that. So if I wanted to find something like that, find the average rate of the plane's change in height, average rate of change, where that height is given by f of x equals x squared plus 5x plus 2. If I want to find this instead of f of 5 minus f of 1 over 5 minus 1, well, this is between time 5, instead of between times 1 and 5, I want between time 5 and something else that's h minutes later. So h minutes later, that would be time 5 through time h minutes later than time 5. Let's call it 5 plus h, whatever that is. So if it's 3 minutes later, it'd be 5 plus 3, 8. If it was 19 minutes later, it'd be 5 plus 19. Why did I pick something hard? 24. But if I want to find this average rate of change, I guess it's x. I was using t to abbreviate for time, but I'll use x since that's the letter that was used in the formula up here. X minutes after taking off the ground, x equals 5 through 5 plus h. If I want to find that average rate over a mystery time interval, I can write an expression for it. It's not going to be a number. It's going to have h's in it, right? But we should be able to do that because what we need to do is the same sort of thing that we did here. F of 5 minus f of 1 over 5 minus 1. Okay, well, I'm going to do f of 5 plus h, mystery expression, minus f of 5, all over, well, 5 plus h minus 5. So, I can't do this. I'm going to use brackets here so that it's easier to see, just because I didn't want to pull up my ugly equation editor. I do 5 plus h minus 5. So change in y over change in x. That would be an expression for it. And like I said, it's going to be something that has h's in it. It's going to be a formula. It's not going to be a number answer. It's going to be a formula with h's. But we should be able to do that. Now, here's the fun with algebra that we need to worry about. Here's our formula for f of x. X squared plus 5x plus 2. So f of 5, I know, f of 5 was 52, right? So most of this ugly looking thing I wrote is easy. The only part that is kind of a mess is that. Other than that, I'm going to have mystery expression minus 52 all over, well, in that denominator, 5 plus h minus 5. That's just h, right? So I can do everything except for what's in yellow right there is pretty straightforward. I'm just going to copy this and say, all right, I've got something minus 52 over h. And the something is this. So all I have to do is figure out what on earth is f of 5 plus h. Well, f of 5, I found by plugging in 5 for the x's. f of 1 I found by plugging in 1 for the x's. F of 5 plus h, in order to find that, I'm going to substitute in 5 plus h for the x's in that formula. And I'm just going to get another formula. It involves h's. And in fact, I don't even really have to simplify it. I can, but let's not focus on that. Let's focus on just what it is. So it'd just be 5 plus h squared, right? That's the x squared, plus 5x, so 5x plus h, plus 2, and then minus 52. All of this, I'm going to make that yellow, is f of 5 plus h, right? So other than simplifying, 5 plus h squared plus 5x plus h plus 2, we've got this done, because we know what f of x is. X squared plus 5x plus 2. So this is just that expression with 5 plus h, replacing each of the two x's. Oops, that's supposed to be 5. Sorry. Nobody corrected me. If I do something silly like that, please fix it. There we go, 5 plus h, replacing each of the x's. 5 plus h squared, 5 times 5 plus h plus 2. Doesn't have a value until I give you a value for h, but for any value of h then, for 1 second past time 5, for 3 seconds past time 5, for 29 seconds past time 5, for 0.03 of a second past time 5. If you had a formula for it, then you could just pop that in for h and go. And that's kind of useful. What these difference quotients are usually used for is to be able to look at a pattern of values around a specific area very quickly, instead of doing a bunch of different difference quotients with a bunch of different starting and ending points. If we just say, let's say I want to talk about intervals of different lengths that are all around time 5. Well, then I can use this sort of expression to do that. All I need to do is just then look at what are the different interval lengths. So what if h was 0.1? What if h was 1? What if h was 2? What's happening to the average speed as that interval gets longer? Is it getting faster or slower? Or what if I think about h getting smaller? What if h is 1, 1/2, 1/10, 1 1,000th? Meaning I'm looking at 1 minute, 1/10 of a minute, 1 1,000th of a minute, whatever fractions I might have said, and what the average speed is over each of those intervals, I can do by just changing the h in this formula instead of recalculating from scratch. Just kind of like with inverse functions, those are useful if, let's say you have a formula for how to find, I don't know, the volume of some complex figure given a side length. And it's this whole big formula. But let's say you're given the volume instead and you want to find this side length. It'd be nice, instead of doing algebra every time you're given a different volume, just make yourself a new formula. If you're going to need to do a computation repeatedly, it's nice to have a formula where the information you're given is in the input position. It's in the middle of the formula instead of having to do algebra every time. So same thing here. Instead of having to do, in this case, maybe just arithmetic every time, we can kind of set this up in advance. If I know I'm going to be finding a bunch of average speeds starting at time 5, then why don't I just write out a formula in advance for average speeds starting at time 5 as the beginning of the time interval, and I can pick the end of the time interval later. So that's generally what these are for. We'll deal with them more later. You'll deal with them a lot more in calculus. So this is not something that's going to be on your test on Thursday, but the average rate of change is. So make sure you keep in mind the average rate of change. And most of the questions in this lesson that I assigned and the homework that accompanies it are really just focused on average rate of change. So you can get some review on that concept, some extra practice at that. Average rate of change is just that slope computation, a difference quotient. All right, so you'll see a bunch of things like, oh, slope between 2 points, and what if the points were closer, and what if I change this length of h? I used h in the example I did just because h is the letter that's used in most math books for the length of this between the beginning and the end point of a generic interval that we'll determine later. But in any case, just take a look at those. It's good practice with function notation, with average rate of change and interpreting it, and, well, a little bit of extra, but not a lot. So the last thing I wanted to talk about today is about your test. So your test is Thursday in class. It is Scantron, so bring a pencil. You need to fill in the little dots. Bring your ID card with you. It's going to ask you for your ID number, but I also need to check your ID when you turn in your test, just to make sure you haven't mutated into somebody else since you registered. I just also need to check you off on everything. Like I said, it's 21 questions, multiple choice. Each of the questions will be counted as 5 points toward your final score. So if you get all questions right, you have 105, this little bonus, in other words, on it, because it's counted out of 100. The topics are from modules 2 and 3, a little bit of everything. Other than, like I said, there's not a difference quotient, and I didn't put any domain questions on there just because both of those are things that we're going to be talking about more later and more in later classes also. So good to have for a starting point, but not anything I want you to worry about. So what does that mean is on the test then? Well, we've talked about, here, open up this review. Talked about using tables and charts to find function values and relationships and constant rates of change or slope. Here's some stuff with compositions of functions. Using constant rates. If you scroll through this, you can see like a little bit of everything. The list of, it's modules 2 and 3 from your textbook, and all the topics are listed also in your syllabus. Writing out compositions of functions, or let's see, here's a volume of a sphere. Now, computation-wise, you could probably get away with not having a calculator on this test at all. I know some of you asked about this. It's not very computational for the most part. There's a couple of little computations you might have to do that involve addition and subtraction of whole numbers and decimals. You are welcome to use a calculator. If you don't have one, I don't think you're going to be at a disadvantage other than maybe an extra like 20 seconds to subtract some one-digit decimal numbers. So it's not anything like you're going to have to take square roots of things and estimate to 3 decimal points or anything like that, or 3 decimal places, 3 decimal points. It's not computational, it's mostly conceptual. Like, here's this, which of these expressions shows the average rate of change? Or which of these statements is true about this inverse function relationship? So a lot of the same sorts of questions where you have to like click the multiple boxes, like things that you've seen on iMath, but not the computational aspect of it, not like compute the average rate of change over 7 days and you have to write it in decimal form to 5 places or something. So there are some more computation things on here. Average speed of the boomerang between time 2 and 3 seconds. The computations involved in that are way harder than anything you're going to see on the test. You're going to see some things on there, but it'd just be basic, like I said, whole numbers and like 1-digit decimals, maybe 2-digit decimal to add or subtract, and that's about it. Let's see, using charts. Here's some more examples of using the problem we just did, compositions of functions, including some inverses, using charts, using graphs of functions to make sure you know how the input and output work, interpreting function notation, what's the meaning of f of 7 minus f of 3, that sort of thing. Like I said, domain isn't really going to be on there. Keep domain things in mind, like what x is and isn't allowed to be. What it is allowed to be is the domain. What it isn't allowed to be is normally what's easier to describe because it's like single numbers or ranges of numbers to exclude. Constant rate of change stuff, delta y equals m delta x. Change in y is the slope times delta x, or m equals delta y over delta x. or we can find new values by starting with initial values and adding on the change. Let's see. Oh, we did a bunch of story problems. Here's Lisa and Sarah meeting at a park bench. They're walking towards one another. We did some tortoise and hare questions where one had a head start, kind of expressing those changes and the distance between people over time, how that's changing. Let's see. Oh, here's a tortoise and hare question. Oh, and the difference between proportionality and constant rate of change. Just as a note here, so tortoise and hare competing in a 400-meter race. The hare lets the tortoise have a head start, and then they run at or crawl at constant rates after the race starts. So the distance between them, the distance that they have to run in the race, how long it takes them to finish, all these sorts of things, we can answer these questions. But keep in mind, like, distance and time in this question, distance between them and distance to the finish line, those are two different things. So just make sure you're careful reading questions about what times or what distances. We talked about this, I think, early on, defining variables. Which ones are we talking about? Because there's a lot of different distances we could be measuring in this question. And it says something about, is D proportional to T? Oh my gosh, what is D? Go back and look. D, the distance between the tortoise and the hare in meters. Ha. And we're supposed to express it for part A in terms of seconds since the starting gun was fired. I want to know if that distance is proportional to time. That one would be, right? Because at time 0, they're a certain distance apart, and then over time, or it's shrinking? Yeah, shrinking because the slower one got the head start. D being proportional to T means that change in D and change in T would have to be the same, but D being proportional to T is that, like, if I take that distance and divide it by time, it always comes out to the same amount. So if their distance is shrinking and time is growing, D and T are not proportional. Those, because one's getting larger and the other's getting smaller. So if I keep dividing different corresponding values of D and T, they should not come out the same, because I start out with a big distance and small time, and at the end I have small distance and big time, and those quotients can't be the same. But the distances, how they change over time, the distances that they've run since the start of the race, those could have something that's related. So if, like, distance that someone's run is getting longer, if they're running at a constant rate, then their own distance and time is those are going to be proportional to one another. That's that slope. But that doesn't mean that the total distance from something else. Be very careful about what we're talking about. So, like, some change in distance and change in time, those are going to be proportional to one another if you're running at a constant rate, changing at a constant rate, whatever the situation is. But the total distance from something, distance between two things, those aren't necessarily going to be proportional, because those aren't the things that have that, those aren't the changes, those are the total values, and those can be growing and shrinking even. So just make sure if it says, are these proportional, that means that dividing different values of them as the problem progresses, whatever it is, over time or over, something is draining, whatever it might be, dividing always gives you the same result. Dividing doesn't always give you the same result in a linear equation either. It depends on, the y's and x's in a linear equation don't always divide to make the same thing. The changes in y and x do. That's that slope. It gives you the same slope if you divide the changes. But the original values don't always come out to be proportional. Interpreting function notation. Not spending a lot of time on the test on algebra simplification. That's not really our purpose here. This was just in here as a, related to things we've had to do to simplify, difference quotient we were just talking about. But in order to simplify some functions and make them look nicer, we do some of these sorts of things, but that's not the purpose of our test. Not the concept of algebra simplifying that we're focusing on. Let's see. I did just post the solutions to this, to all these questions also. If you're interested in those, they're located in the module directly below where this review packet is in iMath. A bunch of problems in here. Trying to think if there's any other topics I haven't mentioned in the last 2 minutes. Express the area in terms of perimeter, express the perimeter in terms of the side length. Rewriting formulas, independent versus dependent variables in a function, what's meant by those phrases, just terminology things. Writing things with function notation. Let's see. There's just there's tons of questions in this. Like there's, I don't know, 50 questions on this review, and some of them have like parts A through G, so there's like 500 questions on the review. I just wanted to make sure there's a little bit of like everything at least, and there's a lot of things that are kind of beyond what our main concepts are, just to get extra practice at them. This is way long. So on Thursday, our test is 50 minutes long, so once we all get started, I'll tell you what time 50 minutes is. We have a longer than 50-minute class period. It's because half the classes for Math 170 meet on Monday, Wednesday, Friday. Shorter class period, we're all taking the same test, so we all get 50 minutes. But all the questions in here should seem like something that we've talked about, just not all of it. Like I said, the test isn't computational in nature, so there's not going to be any of those like simplify this weird algebra expression and do a lot of multiplying out decimals and stuff like that. It's not about the computations. It's about making sure you understand the notation, the definitions, what the relationships are called, like an inverse function or a composition of functions, things like that, and how you use graphs and charts to accomplish same things as what you can do with formulas. Do you have any questions about focus for the test? I don't think there should be anything jarring on there. It should be fairly basic questions in terms of level of difficulty. I'd say this review covers everything like easy to hard, and the test is mostly easy to medium. So the like weird questions that you have like that seem like, ugh, this looks awful, this is going to take me forever and I'm not quite sure I'm doing it right, those are probably not on the test. Now that's not to say that the test doesn't involve you using your brain, but it's not the computational simplification part of math. It's the interpreting part and the making sure you read carefully part, along with, make sure you know the volume of a box is length times width times height, or perimeter of a square. Let's add up the lengths of the four sides, some basic old math, but nothing too fancy. I think the hardest thing, and I haven't mentioned that on here since I think it's coming up on the next page. Distance formula, which is just Pythagorean theorem. I'll probably write it on the board just in case it's something that you don't remember. But it's just Pythagorean theorem rewritten. We've seen box questions a lot. You might expect one of those. Let's see. Vertical intercepts, interpreting vertical intercepts in particular. Absolute values and inequalities. Circles, which distance formula essentially. Let's see, shrinking candles. We've seen a lot of those questions. You might expect to see some of those again. The questions we see repeatedly in the homework, you keep seeing them, you see them in the lessons in the homework, watch for those. So we've seen like what, boxes, tortoises and hares, and burning candles, story problems wise. As a tip, make sure you understand those because, yeah, you're going to see some of those on the test. But you're also going to see, charts. We've seen a lot of those. Yep, you're going to see charts on the test. Those are just kind of more general. Yes?
Will inequalities be?
Not so much, but just like make sure you can interpret between like the expressions and how to write an inequality out of it, not solving and graphing on a number line. That just the whole process, but just can you take this expression and turn it into, we did a bunch of problems with those absolute value inequalities with tolerance. Like a nail needs to be, like a board needs to be cut to, this length, and it can be within 0.05 centimeters of something, or whatever it was. I forget what the tolerance, but those sorts of express the legal lengths as an absolute value inequality. Okay. Or as a compound inequality without absolute values. Okay. And go back and forth between those. So using notation, writing expressions that represent a sentence or a paragraph, a description, written out in words. Key concepts that are really important to being able to do math is turn something that wasn't math into math expressions. Because once you get to that point, there's tons of ways to get it solved, or graphed, or whatever the concept is that needs doing with it, but it has to be translated from sentences into math first. So make sure that you can do that, whether it's write it with function notation or interpret appropriately. So let's see, y in terms of x in terms of y, we were just talking about that earlier. Difference quotient, so the difference quotient stuff, like I said, that's not going to be on the test, probably on your final, but something we'll talk about more later during the semester, and you'll certainly talk about it more in later math classes. Yes?
Will we be given the answers to the review?
Yes, they're posted already, actually. They are right underneath. So I just posted it this morning, but it's right underneath where the exam packet is in iMath. It's right here. And you can, some of them are described how to do the answers, like the long description. Some of them are just number answers, and that's it. If you have any questions about those, you can post them on the forums in iMath. You can go to the Zoom Pathways Tutoring. You can ask people in the in-person math tutoring center on campus, although they are probably less familiar than the Pathways Tutoring if you have a choice between the two. But yeah, if you have questions, figure it out before Thursday morning. Because Thursday we're just going to get in here, get situated. I'm going to get your test materials out to you, and then we're going to start. So there's not review first or something. So make sure you get questions asked and answered prior to Thursday morning. Other questions? All right, so you're going to bring an ID. If you don't have an ASU ID card, as long as you know your ASU ID number, that's fine for the Scantron, but you do have to have some sort of picture ID to show me, whether it's a driver's license, passport, something with your name and your picture, because I'm going to check that out when you turn in your test. But just make sure you're here on time, and we'll get started with your tests, so you have a full 50 minutes and plenty of time to not stress out. All right. Study well, and I will see you on Thursday.